Well, thanks for the great setup. Yeah, so I'll tell you today about some work we've been doing on applications of machine learned flows on gauge fields. Hopefully it'll be clear what that means by the end of the talk. So this is in collaboration with quite a few people over the course of the past 4 or 5 years or so. In particular, I'm going to show you some numerical results towards the end. I wanted to point out that these were done in close collaboration with these two up here, Fernando Romero Lopez and Julian Urban. Okay, so here's basically what I'd like you to take away from this talk. So first, I'll tell you about what lattice QCD is. And so sort of the physics applications of it, and also what it is as sort of a computational problem, so that we can kind of consider that independent of all of the complications inherent in that. From there, I'll tell you about flows. I'll talk about flows some. And so flows, this normalizing flow, is what you should be thinking of. I'll tell you a little bit about the technology we've developed to do flow-based modeling of lattice quantum field theories in general and quantum chromodynamics in particular. And I want to get across, though, that so you've been hearing a lot about generative modeling, basically replacing sampling schemes, other sampling schemes entirely with machine learned components, in which case you would think about a normalizing flow. But flows are more useful than that. Than for just completely generatively modeling a distribution. I want to get across that you can think about flows as a bridge between different distributions in a way that you can usefully use in more general sampling schemes. And so I'll talk about that. I'll show you some demonstrations of just sort of applications of flows beyond just direct generative modeling. So the point I want to get across is how you can use flows as components of larger sampling schemes for calculations. And I'll show you 3 demos of promising use cases we've been looking at in the past month or so. Okay, so what is QCD? So QCD is the part of the standard model that describes strong force dynamics, so how quarks and gluons interact. It's SU3 gauge theory. So QCD, except at very high energies, is non-perturbative. You can't just do pen and paper calculations. You can't do perturbation theory. Instead, sort of the best game in town, if you want to calculate what QCD predicts, is lattice QCD, where instead of doing pen and paper calculations, we discretize the QCD path integral and evaluate it by brute force using Monte Carlo methods. So I won't get in too much into all of the many different applications of lattice QCD, but I do want to point out that maybe you've heard recently about all of these muon G-2 results. And there you can really see how lattice QCD is like a critical component of our modern particle and nuclear physics toolkit. A really crucial role in figuring out whether there's some interesting physics going on there. So hopefully I've convinced you it's important to do these things. So what is lattice QCD more exactly? So the setup is basically we have some 3+1 dimensional quantum field theory. We Wick rotate, and that gets us to 4D statistical mechanics. We restrict our system to a finite volume and then discretize the fields onto a finite lattice, which looks like this, and I'll say more about that on the next slide. Once we have the fields discretized, we have a finite number of degrees of freedom. So our continuous infinite dimensional path integral turns into just a multi-dimensional integral. And what that looks like is this. So if I have some operator O and I want to compute an expectation value of it, it's this integral here. So you have the operator, you integrate over all the gauge fields. And then here you have the weight. So 1 over z, you can't really see this pointer. Yeah, okay. So here, this is sort of the weight of the path integral. So this should look familiar from statistical mechanics. This is a Boltzmann weight. So here S is the action of some particular gauge field. You can think about it as an energy. So as long as your action is real, which it is in a lot of cases of interest, you can interpret this Boltzmann weight as just a probability weight, which means you can reinterpret this path integral as just a statistical expectation value. And you can, just by drawing samples from this distribution P, the target distribution, you can compute expectations in the usual Monte Carlo way. So the way we do this in lattice QCD is we'll repeat a calculation from multiple different lattice spacings and then extrapolate to take the continuum limit. Then we recover predictions of QCD itself. So it's important to note that this is a calculation a framework for doing proper QFT calculations, not simulations. And so it's important for us to retain exactness without in all aspects of how we're calculating this, without introducing any uncontrolled approximations. Okay, so I said I'd say a little more about what the degrees of freedom in our problem look like. I just want to give you sort of a sense of what we're doing or what we're operating on and how big our problem sizes are. So what a gauge field looks like on a computer is it's a lattice of gauge links connecting different sites. So each link is an SU3 matrix, so a 3x3 complex matrix with unit determinant. It's unitary. At each site, there's 4 gauge links because it's a 4-dimensional lattice. Some calculation I'm working on right now, I'm using a 48 cube by 96 lattice. We can count the degrees of freedom in this, and you'll find that this is sort of a nearly billion-dimensional integral. So I think that should give you some sense of scale. You can't possibly imagine doing this without using a Monte Carlo method. So the state-of-the-art algorithm in QCD for sampling gauge fields from our distribution defined by our lattice actions is hybrid or Hamiltonian Monte Carlo. Maybe you heard of it. We invented it originally to do lattice QCD. And the question we've been asking is, can we do better than this using machine learning? Okay, so in a slide, what are the kind of flows I want you to think about? So a flow is a learned invertible map between different fields. In our case, gauge fields, because we want to think about using flows in gauge field sampling tasks. So what that looks like here is if you have some function f, you start off with one gauge field, which I'll just write as u in all of this. You apply the flow, you get something u prime. So the important properties for this function to have, for the flow to have, is that it's, well, basically it's a diffeomorphism. We construct it so that it's invertible, so that the Jacobian determinant, we can tractably compute it, which will let us use conservation of probability. I'll say more on that in a moment. I think you've heard a bit about equivariance. So another property we like to build into these flows is equivariance with respect to our symmetries of interest. This makes them more effective for modeling. And of course, we want to do machine learning, so we put lots of tunable parameters in this, try to make them as expressive as possible. So that's concretely what these functions look like. More abstractly, you can think about flows as bridges between different distributions or theories or actions, which you can kind of think about interchangeably in a lattice QCD context. So what that looks like here is you have some base distribution R. We know what the action is. We know how to sample from it. And then you can imagine drawing configurations from R and then drawing an ensemble of configurations from this distribution using whatever sampling algorithm you have. And then applying a flow to all of them. This will induce another distribution if you look at the new ensemble you have, which we'll call Q, the model distribution. And because the flow is invertible, you can map configurations back and forth between R and Q. So in that sense, the flow provides an exact bridge between distributions R and Q. We don't get to choose what R is, or we get to choose what the base distribution is. We don't get to choose the exact form of the model distribution because it's induced by this learned flow. So for sampling applications where we have some distribution we're interested in, instead what we'll do is variationally optimize the flow so that our model resembles some particular target that we're actually interested in. Then the flow is or serves as an approximate bridge between the base distribution R and the target P. Okay. So this slide is basically reviewing what generative modeling is in the usual context. So image generation sort of looks like this. In a way, I'll explain a bit more. But this is sort of the simplest possible way you can think about using a flow as a bridge to do QCD sampling. The idea is you can sample from a really simple distribution. So like spiritually, the equivalent of like a bunch of Gaussians for gauge fields is a bunch of uniform distributions on the gauge link. Our uniform is just the SU3 generalization of uniform. So you think about taking your Haar uniform distribution, which we can sample from exactly. You draw samples from it, You apply a flow to them, and that gives you samples from a model distribution. We can draw independent samples efficiently from our base distribution, so we can draw independent samples efficiently from our model. From there, we don't want to compute expectations under our model. Like I mentioned before, we want to do calculations, not simulations. We need to be able to control all of our sources of uncertainty. So the way we handle that is just by reweighting. So with a flow, we can compute the density. Sorry, I completely glazed over this on the last slide. The model density, this is important. We can compute the density of the model distribution in terms of the Jacobian of the flow. So as long as you structure your flow so that that's computable, you can do that. Okay. Given that model density and given your known target density that you actually want to compute expectations under, you can just compute reweighted expectation values. So we can compute the reweighting factor for each configuration just by dividing the target density by the model. And then you can recover your expectation value just by plugging in the reweighting factor alongside whatever observable you want to compute. So this costs you your reweighting factors, unless you have a perfect model, have some variance, and this will add some variance to your expectation values. You can quantify that by looking at this metric called the ESS, or effective sample size per configuration. It falls between 0 and 1. 1 is perfect, 0 is very bad. And you can think about it as quantifying how much your variance increases by having to do this reweighting versus if you had a perfect independent sampler. If you're doing Markov chain Monte Carlo, you've maybe heard about the notion of an autocorrelation time. It's related to the ESS in this way. 1 over twice the autocorrelation time is roughly the ESS. This will be useful later. So in order to build up to doing this application, so generative modeling of QCD, the QCD path integral, we've been building up all of the various components we need to do this over the past 4 years. And so I won't tell you too much about this. You can check these references if you want to know more. But I'll note that the important components in this were, so usually when you're thinking about normalizing flows or diffusion models, you have some real valued degrees of freedom that live in -infinity to infinity. For us, our degrees of freedom are gauge lengths, which live on compact manifolds, specifically SE3. So in order to treat that, we had to figure out how to construct flows on compact manifolds. We also had to, so in lattice QCD, there's SE3 gauge symmetry. This is a really high dimensional symmetry group. If you think about trying to model some distribution that has this symmetry without encoding this exactly, it's clear that you're going to have a really hard time constructing a high quality model. So instead, we figured out how to build the models or build the symmetry into the models explicitly. We've had to work out some approaches to doing stochastic methods to treat fermionic degrees of freedom. We've also explored some how to do self-training of these models. I'll say a little bit more about that later, and also how we can reduce training costs with transfer learning. So this is sort of how the program is built up. And recently, just last summer, we put all of these things together and did a first demonstration in QCD of direct generative modeling of the QCD path integral. But sort of the state of things now is that the models we can construct aren't quite high quality enough yet to enable direct generative modeling of QCD at our parameters of interest. So we're making a lot of conceptual developments lately and a lot of improvements in the quality of our flow models, but we haven't enabled this sampling application yet. So this sort of naturally raises the question, given the kind of flows we can construct now, what sort of sampling can we do? How can we make use of these productively? So I'm going to show you some demonstrations now. So a few technical details on it. So instead of doing QCD, I'll look at just SE3 gluodynamics, which is just sort of a simpler model system for QCD. The architectures I'll be using are these things we call residual flows. I won't get into any of the details, but you might think it's interesting. And I encourage you to look it up if you do. The idea with these is they look like an ODE flow. They use transformations like an ODE flow, but they combine it with variable partitioning like you might do in like a real MVP coupling layer type model. which lets us compute a tractable and inexpensive exact Jacobian in the same way as coupling models while encoding symmetries in a natural way, the same way you can with ODE flows by parametrizing an invariant potential. So we have equivariant flows. The flows are translationally invariant, which lets us sort of transfer between different lattice volumes, which is useful for reducing training costs. And I said earlier that I would mention a little more about how we actually train these. So sampling is generally expensive in lattice QCD. Like I mentioned before, we have these really high dimensional integrals. So you might ask, without a giant pile of training data, how can we train these? And the idea is we have the model train themselves. So they draw samples, and then we use the samples from the model to estimate a KL divergence and then minimize that. So we only require model samples to train. We don't have to do any external data generation. And yeah, so an important aspect of this approach is that we can train on smaller volumes, like I mentioned before, and then transfer, which lets us cut down on our training costs. Okay, so, okay. On to the first application. I'll use all of the things I just told you in all of these applications. So first idea is correlated ensembles. So the idea is, imagine you have some base distribution R. It's some QCD at some parameters of interest, say. You generate a bunch of gauge fields, so you've sampled an ensemble from this distribution. You can consider now taking each of these gauge fields and applying a flow to them. You get a second ensemble, a float ensemble. These two ensembles are correlated. This is useful. So you can make use of this, for example, to get correlated noise cancellation when you compute differences. So suppose I have my target distribution P, my base distribution R, QCD at two different parameters, and I want to compute the difference in expectation values between those two theories. So I can write that just as these two expectations in the top line. I can rewrite the first expectation under the target using my reweighted flowed model version. And then by plugging in the flows explicitly, I can rewrite this whole thing as just one expectation under the base distribution. So you can kind of see how that would give you correlated noise cancellation. Instead of computing two independent expectation values, you can just compute one. So there's a lot of ways you can think about exploiting this usefully. One of them is so one of them is just in taking continuum limits, that sort of thing. Another one is in calculations that make use of the Feynman-Hellman theorem, which you might remember from that one homework problem in undergrad quantum mechanics. So the idea here is you take your lattice action and you perturb it by or add some small perturbation, some current O, and with some parameter next to it, lambda. Then you compute the energies of some hadron. And specifically, you can compute the derivative of those energies with respect to this perturbing parameter. And this will tell you something about hadronic matrix elements of this current. So correlated differences look like derivatives, so this is sort of an obvious application. So we went ahead and tried this. So specifically, we tried it on this approach by this group to use the Feynman-Hellman theorem to estimate something called the gluon momentum fraction of the pion. You don't need to worry too much about what that means physically for the purposes of understanding this demonstration. The idea is you perturb your action by introducing a spatial temporal anisotropy. And then you can relate the derivative of the pion mass with respect to the anisotropy parameter to this physical quantity we're interested in extracting. So for this demo, we just decided to keep it simple. And we estimate that derivative with a forward difference. So just the mass at lambda for some finite lambda minus the mass at 0. We tried this out on these parameters. I don't expect these to mean too much for you if you don't do lattice QCD, but these are sort of small by modern standards, but not too small to do physics on. The flow we trained, we just train a flow to go from lambda equals 0 to this perturbed distribution with lambda 0.01. Okay, so how do we do the calculation? How do we assess whether we've gotten some computational advantage from using the flow? So here's 4 different ways of estimating the pion mass. One of them is just at lambda equals 0. So this gets involved in the 3 different ways I'm going to show you of estimating this. Another one is you can just reweight epsilon away, where epsilon in this case is 10 to the minus 6, and compute the pion mass there. And that's one way you can get 2 pion masses to take the derivative. Another is with this float approach. So we generate an ensemble at lambda equals 0. We flow that ensemble to finite lambda using the model, and then compute the pion mass there. That's correlated with our original pion mass. You can also instead generate a completely independent ensemble at lambda 0.01. And so those are sort of the 3 approaches we pursue. And we compute this quantity, this difference. And these are sort of the 3 different results we get. So in the middle, we have our flowed result. On the left, we have the result of computing this difference using our epsilon reweighted mass estimate. And on the right, we have it with these 2 different independent ensembles. You can see that the correlated noise cancellation has bought us something. Versus the multi-ensemble approach, we get a factor 4.5 error reduction. So the noise cancellation, even at matching statistics, has given us a big advantage here. Versus the epsilon reweighting approach, which doesn't require a flow or generating an independent ensemble, we still get a factor of 3 error reduction. Okay, so interlude before the next 2 applications. So in lattice QCD sampling, we have this sort of sampling problem that prevents us from going to finer lattice spacings. It's called topological freezing. The idea is that the gauge field distribution that we want to sample is multimodal. And because we're using Markov chain Monte Carlo algorithms to sample it, you can think about MC-MC algorithms as sort of smoothly exploring the phase space of your theory. It can get stuck in different modes. And as the modes become more and more separated, the time to tunnel between them can grow exponentially. And indeed it does as you try and go towards the continuum limit. So this sort of just shows what that looks like. The Q here is the topological charge, which diagnoses what sector you're in, which mode you're in. And this just shows sort of time series at 3 different parameters approaching the continuum limit. And you can see that even as we change our lattice spacing just a little bit, the rate at which this charge mixes slows down very rapidly. So the issue that arises here is that if you don't deal with this problem, if you have this mode freezing issue, it can result in basically an effective loss of ergodicity, which can result in sort of a really subtle failure mode in these calculations. Specifically, you can get apparent convergence in your Monte Carlo estimates to wrong answers. So that looks basically like this. So this gray stream here, on the x-axis, it's sort of the sample size we're using in an estimate. So you expect this to converge to the true answer with small errors as we crank up the stats. So if you have unfrozen sampling, it looks like this blue line. We converge to the correct answer smoothly. There's no issues. If you have this mode freezing problem, it looks like this gray line. So you can see the errors are getting smaller. Everything looks fine, but it's just completely wrong. The way this announces itself is as you keep sampling, eventually you'll see the stream tunnel between different modes. And when that happens, your estimate will sort of catastrophically correct itself. But until this happens, you don't necessarily know that you have a problem. So this is sort of a significant issue that really needs to be addressed carefully. So how can we deal with this? So the direct generative modeling approach I proposed or discussed before is one way, but how can we deal with this without having to do full generative modeling? And the idea, or an idea, that originally came up in the condensed matter context, see this reference, is to use parallel tempering or instead replica exchange with flows. So the idea of a replica exchange algorithm is instead of sampling from one distribution, you sample from several distributions simultaneously. And you consider sort of a family of those distributions interpolating from easy to sample parameters to hard to sample. So here the interpolation is just 2 points, but this sort of generalizes to more in a natural way. The idea is you evolve each one of your independent Markov or each one of your Markov chains independently, and then you propose swaps between the distributions. And here, so you can do this without flows, but here we're using the flows as sort of a bridge to enable this swapping and to improve the rate at which swaps occur. And so this is sort of the acceptance probability you have to apply. So you propose these swaps and accept or reject them. We don't have to dig into this too much, but I did want to point out some limiting cases. So if you have identity flows, your flows don't do anything, then you recover just unflowed replica exchange. If you have a perfect flow, the swaps are always accepted. So 100% model. And as a limiting case, if you have a two-chain system, or if you're sampling two chains at once, and beta equals, or the easier one is the hard distribution, or your simple base distribution, you recover this full generative modeling example I discussed earlier. So this gives us a way to recover those capabilities smoothly. Okay, so we went ahead and applied this, and I'll just walk you through this really quickly. So this is on the bottom panel, this is the same thing we showed before. With as we go to harder and harder parameters, our topological mixing slows down. If we just do unflowed replica exchange and try and sample the three of these simultaneously, we'll find that these even closely related distributions, we get basically 0% swap acceptance rate between. But by putting in flows, relatively simple ones, we were able to increase this to sort of 15 to 20%. And you can see the effect here. So all of these chains are visibly mixing much faster, which is good. We can try and be a little more quantitative about that. And so what these plots are is, so I mentioned earlier the integrated autocorrelation time. Your sampling costs are sort of linear in that. So we want this to be lower. We can estimate it by just integrating up our autocorrelation function. So you expect these to plateau at the value. And just what to take out of this is, if you look at just the heat bath case, so just sampling each distribution individually, you see this clear hierarchy between the autocorrelation time, so it is slowing down. Whereas with these flows enabling the replica exchange, with the swaps, you see that this hierarchy sort of collapses and all of the autocorrelation times are reduced. And even the fastest mixing chain in the unflowed case is slower than the slowest chain in the mixing case. So if you're interested in sampling all three of these theories, this is sort of an unambiguous gain, neglecting the costs of having to apply the flows. Also note that these three streams on the left without the swapping are uncorrelated. The swapping induces correlations between the streams, which can be useful in sort of the same ways I discussed before. Supposing you were only interested in sampling the most difficult stream, and the other two streams were run as sort of you intend to discard them after, then we have to pay sort of a factor of 3 overhead, because we're doing 3 times as many streams as just directly sampling the target theory. And so accounting for that overhead, this is still sort of break even. So we haven't solved topological freezing in that sense. However, you can imagine if we can establish bridges between more separated theories, we can actually uncover a real computational advantage. So I'll move on finally to
just a quick question, if you don't mind.
Yeah.
So I'm familiar with the U1 in 2D result from a few years ago with flows that didn't use T-Rex U1 in 2D.
Yeah.
I'm just a little turned around. What theory and dimension are you in here? And
oh, sorry. So this is 4D SU3.
SU3 Yang-Mills.
Yeah, 4D SU3 Yang-Mills.
4D SU3 Yang-Mills. And do you have, so I understand you have the flow T-Rex compared to the T-Rex, but do you have just like the 4D Yang-Mills analog of what was done in the U1 and 2D paper for comparison?
Yeah. So this was sort of some of the earlier demos I mentioned. The difference is this is on way bigger systems than we can treat with the analog of that approach right now.
So you just can't even attempt it.
I mean, we can attempt it. It just won't work very well yet.
Okay. But whereas this is already working pretty
right.
well.
Yeah. So this is like on, yeah, I guess I should have mentioned these, like the lattice volumes here are sort of, this one I think is 12 to the 4th, which is, you know, many, many, many times bigger than what we've been able to demonstrate with direct generative modeling so far.
That's great. And so I guess in that first paper I mentioned is a couple of years old, but you've really scaled up to a better theory than U1 in 2D, and you're
Yeah, no, this is right in the neighborhood of what
that's
we
real
actually
progress.
want to do.
Yeah.
Like we're almost to the point of doing something computationally advantageous.
Great. Thank you. I understand.
Okay, so last application. So still T-Rex, still flowed replica exchange. But instead, we're going to consider operating with the flows only on a subvolume. So the more degrees of freedom you need to treat with a flow, sort of the harder things get. And so instead, what we can think about doing, instead of applying the flow to the whole lattice, is we can imagine applying a flow only to a subvolume. And so what can we do with that? So what we can do is, if you imagine taking your lattice and introducing a localized defect in the action, so you sort of take your quantum field theory, pull out a patch of space-time and replace that patch with a theory that's easier to sample. This can sort of speed up your mixing rate across the entire lattice. But you aren't really interested in sampling the theory with a defect in it, so you need to remove it. So there's this approach that's been proposed independent of flows to do this and use just replica exchange, interpolating between a defected theory to the theory of interest, and you use replica exchange to remove the defect. So the natural question then is can we remove the defect more effectively using replica exchange? And this lets us, this is a natural application of the case where we want to flow on subvolumes. So the idea is we train a subvolume flow to repair the defect. So the flow acts in the neighborhood of this defected block and then just tries to map to the theory that does not have the defect in it. Sort of what the geometry of that looks like is, you can imagine this dashed box is sort of the whole lattice. We pull out a chunk for the flow to operate on. It has some sort of frozen context around it that we use to condition sort of the boundaries, so it knows how to make something that it can stitch back into the lattice. Then it has some region around the defect that it operates on. And so that's sort of what the problem looks like. Another advantage of this, other than having to treat fewer degrees of freedom, is that you can operate on the same size subvolume in any size environment. So you can imagine, maybe flows are expensive to apply, but if you're only operating on a very tiny subvolume while sampling a much larger volume, maybe the flow costs will trivialize. So we went ahead and applied this to some challenging target on an even larger volume still, 16 to the fourth. We introduced a size 2 defect. We tried to repair it in 2 hops, and we were indeed able to do that. The flows acting on an 8 to the fourth subvolume managed to enable a swap rate of sort of 20 to 30% between the 2 streams. Without the flows, the swap rate was, I didn't see any accepted. So this is sort of a massive improvement in that sense. To be fair, you can get similar swap rates, so 20 to 30%, by considering only 7 to 8 chains instead. So in that sense, this is sort of only a factor of 2 improvement right now. I'll point out that, so on the bottom, without any swapping, you can see the topological charge mixes very slowly. On the top, you can see, again, it looks much fuzzier. This is good. But if you look a little closely, you can see kind of, you can convince yourself that probably what's going on here is mostly just the swapping. So we do need to be a little more quantitative to determine whether this has actually given us an advantage. So we measured the autocorrelation times with swaps on the right with the defect repair flow. It is indeed lower autocorrelation time in each of the 3 streams we were looking at. But in this case, because 2 of the streams are these defected theories, which we're not physically interested in, we have to pay a factor of 3 overhead because we're running all of the evolutions on these streams. So this is still sort of at the break-even point. But this is sort of our first demonstration. We know where we need to go from here to demonstrate a computational advantage. The general method has been shown to work in other cases. We just need to go to deeper and wider defects to make this work. So there's sort of a clear machine learning target to move to from here. Okay, so that was everything I wanted to show you. So just to close, so there's sort of a lot of different avenues to work towards to accelerate lattice QCD calculations. There's sort of a lot of room for creativity. I just showed you a few examples of ways you can think about using them, but you can imagine that there's many more opportunities still. I wanted to point out that this replica exchange idea recovers in a certain limit direct sampling or direct generative modeling. So this can let us work towards the generative modeling case, which is sort of the holy grail, and get useful improvements before that's possible as we develop better and better flow technology. Replica exchange isn't sort of the only game in town for considering these sort of annealing trajectories between theories. There's also a large family of algorithms, I think the most general of which one I know is Craft. It has a subcase called stochastic normalizing flows, and those look a lot like the diffusion models we've heard about today. Yeah, and this replica exchange, the defect repair thing I showed you at the end, this looks really promising, even though we haven't been able to demonstrate a computational advantage yet. We've only been working on this for a few weeks, and I'm optimistic. So yeah, thanks very much.
A lot. Questions for Dan?
One of the things to be careful of, and I'm sure you're aware of it, but you have two samplers that both are very long correlation times, and then you mix between those two samplers, you get you get a sampler that might look like it has a very short correlation time, but actually just because you're randomly kind of exchanging between the two doesn't really
yeah, that's what I was trying to get at with pointing out that these look fuzzier, but you need to be a little more careful. Yeah, thank you.
I also have a question or two questions. Not sure they make sense, but still, you have this issue that this flow is relatively slow to run it at test time, is my impression, right?
I wouldn't say relatively slow. Like there's no numerical integration. It's just sort of they're not free. The flows we're using now are more expensive than a single step of the sampling algorithm we've been using for this test theory. But if we actually went to do QCD, HMC is more expensive than the algorithm we can use for this. So the hierarchy would be reversed, but it's also not clear whether flows of this size are what we need to do. So sort of the timings, relative timings aren't clear yet.
So it's not a bottleneck in that sense.
Not necessarily.
Okay, fair enough. The other question is, so you are using flows related to this diffusion model literature. Some people develop like some of these Schrödinger bridge type methods to bridge general distributions, which is a bit more inspired by the diffusion model stuff. Is that something you could use potentially to replace flows? When you train those methods, I don't think you have to backprop, so the whole flows end to end and all this kind of stuff.
Yeah, I've been trying to think about this. But we have this sort of strong constraint where we need to be able to estimate the density exactly. And basically everything other than normalizing flows, you only get an approximate density, and that'll induce some approximations that basically we can't really get away with if we're trying to take a controlled continuum limit.
I see, thanks.
Other questions for Dan? I have one more. You sort of implied with your setup that the flows story is more general in lattice than anything having to do with normalizing flows being applied. Could you comment, are there on interesting cases where just by being clever, people come up with maps F between distributions that might help you solve certain theories? Are there cases like that where people just try to do it directly theoretically? I've heard the phrase trivializing flow, but I'm
yeah, I mean, so there's sort of this whole line of research kind of picks up after something that was explored basically 10 or 15 years ago now, where basically you can write down an exact ODE flow that if you integrate it infinitely will trivialize your gauge theory. And so they experimented with that and found that it wasn't able to provide a computational advantage in the way that they were using it at the time. So there are analytic constructions. They're just not necessarily useful, and we're sort of building up from that.
And from what I understand, they're not useful in the theories of interest, 4D QCD, but are there interesting theories where they are useful, or is it just sort of generally
So I mean, they're not completely, they don't provide a computational advantage for sampling. They are useful for a lot of other things, I should say.
I see.
I also, yeah, I don't think I'm prepared to comment that generally.
Excellent. Well, I was just curious.
Mhm.
It seemed like that's sort of what you were implying, that this is a pretty general concept.
Yeah, I mean, it is.
All right. Well, let's thank Dan one more time.